We're now on the second page of the notes from section 7.3, page 46 overall. And here we're going to use the shell method. So we're being told here to use the shell method to find the volume of the solid obtained by rotating the region under the curve y equals sine x squared for 0 less than or equal to x less than or equal to root pi about the y-axis. Okay, so that's a vertical axis, and again we cannot change this to x equals a function of y, at least not in a nice easy way. So what we're going to do instead is shell method, and let's look at what this function looks like. So I'll kind of help you out here because you've probably never graphed sine of x squared. We know that sine of pi is 0, so like it looks like x would have to be root pi in order for that to work, and that's why we see root pi right there. And now sine of 0, that's still the same. And now it comes up here to a height of 1 before coming back down like so. And in case you're curious, this happens at root pi over 2, where it achieves a value of 1. Since when you square it, you just get pi over 2, and sine of pi over 2 is 1. All right, so we're going to take this region. Notice it's bounded below by the the x-axis, and we're going to spin it here about the y-axis. And so what we get is actually quite similar to the picture in the last video. Good enough, I guess. Okay, so using shell method, this is our idea, class. So what we need to do is for every x value, we need to make a cylinder from this. Well, the region here, this is the height of the cylinder on the region, and now we get something like this. Okay, so there's our cylinder, right? And now once we figure out the area of that cylinder, the surface area of that cylinder, we just integrate from 0, which is the left x bound of the region, to root pi, which is the right x bound. Okay? So let's see if we can figure this out. So we're going to get the volume then equals the integral from 0 to root pi 2 pi, and now let's see, the radius of this cylinder is exactly given by this x value, right? This is 0, this is x, so that length there is just x. And now the height of the cylinder is exactly given by the height of the function, which is f of x, which just so happens to be sine x squared. Okay. Now, what you'll observe is that to integrate this, don't just start doing normal antiderivatives with x squared over 2 and blah, blah, blah. You'll notice here that we're multiplying these two functions. So maybe let's try to look for a u substitution here. If u equals x squared, then du is 2x dx, which we're seeing a 2x and a dx. So I think that's maybe the right thing to do. So let's put this problem on the back burner and instead just do this antiderivative really quickly. Well, we're going to set u equal to x squared. Du is 2x dx, which dx then is du over 2x. And so we get the integral 2 pi x sine u, and then dx is du over 2x. X cancels, and 2 cancels. And so we just get the integral of pi sine u du. The antiderivative is, of course, negative pi cos u. And then technically there's a plus c here, but we're not going to need it because we're going to be doing a definite integral. And then back substituting, we get negative pi cos x squared. All right, so now let's actually find the answer to the problem at hand. The volume is then well, we just did the antiderivative. We have it right here. So that's minus pi cos x squared, and we evaluate from 0 to root pi. So plugging in root pi, we get minus pi cos root pi squared, minus parentheses, plug in 0, minus pi cos. Okay, we get 0 squared here, but that's just cos of 0. Now this is not 0, class. This is cos of 0, which is 1. So we have a double negative, so that'll actually turn into a plus pi. And here we get minus pi cos pi plus pi times, and remember cos of 0 is 1. Cos pi, think about it really quickly. It's negative 1. So we get negative pi times negative 1 is positive pi, plus 1 more is 2 pi. All right. So now what we're going to do is let's pretend we have now a region that's bounded by multiple curves. So drawing a graph here, we have y equals x squared and y equals x are our two curves, and we're rotating about the vertical axis, which is the y-axis. So what we get is, well, we've graphed these multiple times in the past, so I won't belabor what their graphs look like. That's x. This is x squared. And now we're rotating here, class. And so we've probably seen this picture or something like it before. Only now we're not going to be using disk washer. If we wanted to, you would need to convert everything to a function of y, which is actually not that hard to do. X equals y, x equals square root of y. But we're instead going to use shell method and show that we would get the same answer. And I encourage you to actually check that both disk washer and shell method will give you the same answer. So the way we're going to do this now is we're going to pick an x value. And what we need to do is find the surface area of this cylinder that I'm going to draw for you here. So hopefully it's clear what we're looking at. All right. So then the volume of the solid that we get is the integral from 0 to 1, which are the x bounds of the region. So shell method about a vertical axis, you have to use x. All right. So it's sort of backwards from disk washer. It's 2 pi. And now let's determine what the radius is. The radius is, well, it's the distance from 0 to x. Well, that's just x. And now the height of the cylinder, this is where things get a little bit interesting here. The height of the cylinder is not just x, it's x minus x squared, right? It's just that little sliver right there. And of course dx. All right, well, distribute, we get integral 0 to 1, 2 pi bracket x squared minus x cubed dx. The antiderivative is 2 pi x cubed over 3 minus x to the 4 over 4. And again, we're using the x bounds of the region, which are 0 to 1. And so at long last here, we plug in 1. I think we're just going to get 1/3 minus 1/4. And then we plug in 0, and I think we can see everything is 0 there, right? Common denominator is 12. Here I get a 4, here I get a 3. So that's 1/12 times 2 pi, which is pi over 6. Okay, so that's it for this page. In the next video, we'll do a little bit more rotating about a vertical axis that is not the y-axis. So we're going to move the vertical axis around.